All right, welcome to chapter 10, part 1. This is a shorter chapter, only one real new reaction and two mechanisms. So let's dive in. We're going to be looking at radicals. And so that we understand, where we're starting from, right? A radical is simply an atom with an unpaired electron. Right, so we're going to see carbon radicals and halogen radicals and oxygen radicals, but it's any atom that has an unpaired electron as opposed to like a lone pair. So we've been dealing with a lot of reactions where when bonds break, we get a heterolytic cleavage, right? We've seen that quite a bit between, let's say, two atoms where the bond breaks and then you wind up with one has a plus charge, one has an extra lone pair, and a minus charge. When we get a homolytic cleavage, where one electron goes with X, one goes with Y, you wind up making two radicals. And so we will see some homolytic cleavages in today's mechanisms or in this chapter. It's very important that when you are drawing arrows for me, say, for instance, in like a lab where I ask you for mechanisms, that you either do a single barbed or double barbed arrow, whether you are moving two electrons or one electron. It's important, right? It's an important detail. When you are doing your homework, you have the option between both kind of arrows. And so it's important, if you want to get the right answer, to use the right one. When we think about a radical, before we get into the, reactions, we just think about the geometry of a radical. It's somewhere in between a carbocation and a carbanion, right? So we think of a carbocation as being flat. We think of a carb anion as still having that sort of trigonal pyramidal geometry, and a radical somewhere in between. That can sometimes lead to some interesting stereochemistry. A lot of times we think of it more as the flat, but the reality is it's somewhere in between trigonal planar and a very shallow pyramid. When we think about stability, we are going to see the same trend that we saw with carbocations, right? So your stability is the same trend as your carbocations. So your tertiary radical is going to be more stable than secondary, more stable than primary, more stable than methyl. Resonance also plays a role. So, for instance, if we had this radical, this primary radical versus this primary radical, this one's more stable. And it's because you actually can have resonance with radicals. Because think about what a resonance structure is. All of the atoms are in the same position, but the electrons are distributed differently. So if I do a homolytic cleavage of the pi bond and move that radical in, right, there is resonance. So it's all of the same trends that we see with a carbocation, right? The more R groups that are nearby, the more stable it is, and then it can also be stabilized via resonance. And this is just a little bit of quantitative analysis of that, what we see here on our stability. So if tertiary is the most stable radical, methyl is the least stable, we see that breaking the bond for methyl is actually higher in energy, right? So it's harder to make that radical than, say, the tertiary one, because what you get on the other side is indeed more stable. So it's just a little bit of quantitative analysis there. Oh, and I knew this slide existed. I just wasn't sure where it was coming. But so it's just another way to show you, right? Radicals can also experience resonance. Again, it's just a distribution of electrons. and resonance is always stabilizing. Here's another look at why a benzylic radical, so a radical on the carbon next to a benzene ring, is actually quite stable because of resonance. And again, just some quantitative information there. Okay, now something that is different though. You have the same trend as a carbocation, but they do not rearrange. So no rearrangements in radical mechanisms. I did not give myself enough room there. All right, so that's a big key difference. This carbocation can do a methide shift to make a tertiary carbocation. This one, however, they don't rearrange, so there will be no shifting. Now, when we get into specific reactions, there are different patterns that we are going to see. I'm going to go through these relatively quickly because I'm more interested in looking at the actual reaction. But most patterns, trends in these different categories. One, homolytic cleavage. We've got to form a radical somehow. There's usually some sort of initiation. The delta symbol stands for heat. HV stands for light. You're going to see that quite a bit today. Then you have radicals, which are very reactive. Unpaired electrons tend to be much less stable and very reactive. So they will react with double bonds. They will react with hydrogen. They will react with halogens. And so we're going to see some of these steps in the mechanisms that we look at today. There are also, so there's these four. So the homolytic cleavage, like the initiation of the radicals, the radical reacting with a pi bond, or not a proton, a hydrogen, and a halogen. You also get a type of reaction called an elimination, where a radical will behave in a way that causes a leaving group to leave. I'm not sure we actually see that step in our reactions today. And then coupling reactions. This is an important final step that happens in a lot of radical mechanisms. When two radicals run into each other, they frequently form a bond because, again, they're both very unstable. They're both looking for a partner, right? The electrons would rather be paired up. Okay, and so here's just a summary of those different processes. So what we're going to be more interested in is the steps to our reactions. So when we have a radical reaction, it is typically split up into three basic steps. Initiation, so getting your radical formed. Propagation, this is where we spend most of our time. A radical reaction is often a chain reaction. Once you start it, once you get it initiated, it keeps itself going. And so essentially this is where we form radicals. Propagation is where you're going to have a radical on both sides of the equation, right? So you have a radical at the start, it reacts and forms another radical, right? So you have something really reactive, it forms something else that's really reactive. And then lastly, termination. So in termination, we basically destroy the radicals or use up the radicals. So there's no more radicals on the other side of a termination step. If we look at those patterns that were previously shown, homolytic cleavage is the only initiation step. Most of the steps are propagations, where you'll notice we have radical, radical, radical at the start, radical at the finish. And then the termination is that coupling step where two radicals come together, they pair up their unpaired electrons, and then there's no more radicals. This is usually the end, right? Hence called termination. So the new reaction that we are going to be really interested in, this is something that we did in lab, but we did a slightly more complex version of this, is radical halogenation. Right? So what we are going to be doing is replacing a hydrogen atom with a halogen. So whatever is attached to this carbon, there is also a hydrogen. So we're going to start off looking at methane, but this will go for any sp3 CH bond that we might encounter. We are going to react it with a halogen. It's going to either be chlorine or bromine, and we'll talk about the reasons why as we move forward. And light. So there has to be something to initiate it. If you just throw in Cl2 or Br2, nothing will happen. The light is critical. And we will replace that H with the halogen, and we'll make a little HX byproduct. Right? So this happens in our three groupings of steps. So let's go through the mechanism. I'm going to write it as I'm talking, but it is also on the slides. All right, so first step is that initiation. Your methane is not even involved. You're going to take your halogen. So I'm going to just use X because it works the same with bromine or chlorine. And you are going to apply a certain wavelength of light. That light is going to cause this bond to break homolytically. And now we have two halogen radicals. Now, a lot of times you're going to notice that radicals, you can put in all of the lone pairs, but frequently you're also going to just see them drawn, let me show up here, with just one unpaired electron, because that's the one we're really interested in. But you should know a halogen also has 3 lone pairs. Okay. Now from here, once your halogen radical has been formed in that initiation step, it moves into propagation. So that halogen radical is very reactive. So if we're dealing with methane or any other sp3ch here, it is going to react and cause that CH bond to homolytically cleave. So there is where we form our HX byproduct, and we are left with a very reactive carbon radical. The carbon radical is what moves on. So for whatever reason, the steps of the radical mechanisms are shown individually rather than as like one story. If you are doing this for your lab, for instance, that's due this week, you could just continue it on. But I'm going to follow Klein's lead here, and I'm going to bring this down. So we had X2, but there's a lot of reasons here why you're still going to have X2 in your reaction mixture. Not all of it was initiated, not all of it cleaved. Sometimes the two radicals find each other and reform. There's different reasons, but you're going to still have X2 in that solution. So when your carbon radical runs into it, X2, it causes a homolytic cleavage of the halogen bond. And this is how we get our product, right? We've made our new CX bond. And if you'll notice, we've made another halogen radical. So that halogen radical can go on to react with the next molecule of your organic starting material. So you don't actually have to do a lot of initiation. As long as some radical is formed, once it gets to the propagation step, it will keep itself going. And then finally, for this reaction to come to an end, you're going to get termination reactions, right? When you have radicals around, they are very reactive. And so what really brings this to a close is anytime your There we go. Anytime your radicals run into each other. So for instance, if two of your halogen radicals were to run into each other, you would make a little bit of X2, which can go back into the reaction. If your carbon radical runs into your halogen radical, right, this could form a little bit more product. Just put it there. And there's even a small chance that two carbon radicals could interact, in which case you might get a little bit of another organic byproduct where your two carbon groups came together. Now, what's going to be present in the greatest abundance is going to be your halogen radicals. So for the most part, most of your termination is going to occur when those halogens run into each other. And then this just gives you more of your product. This last termination step here just shows you one impurity you might get from this reaction. Now, the propagation steps are really what show you kind of the overall reaction. If you add them together, kind of like an old Hess's law problem, you wind up getting your net reaction. The initiation and termination steps are really just dealing with making the radical and then using them all up at the end. It's also why this is called a chain reaction, right? The products in the last step are also the starting materials in the first step. Chlorination is one that is difficult. You will start to notice that all of your practice problems use bromine. And so one of the reasons for that is twofold. One, it's difficult to stop chlorine from adding multiple times. So if you're just trying to add one chlorine, this can be very difficult to do. It's also not I won't get ahead of myself. So polychlorination is one reason. Let's see. Okay. We'll follow Klein's lead here. There are different ways to initiate radicals. Heat and light are very common. One thing you might recognize here is a peroxide. Peroxides are easy to initiate for radical reactions as well. That'll be important when we talk about our anti-Markovnikov addition reactions in the second video of chapter 10. There's the things that can initiate, right? Things like light or heat. We used a chemical initiator in lab, AIBN. There's also things that can inhibit radicals. And this is more of a kind of a practical discussion we're going to have for a moment here. So oxygen, O2, is actually a diradical and can react, it's very reactive, with a number of different things. It's responsible for a lot of aging. And so a lot of things that we look at for either anti-aging, for our skin, for our bodies, for our foods, are called antioxidants because they react with these oxygen radicals. This is just one example of a radical inhibitor. Radical inhibitors behave by reacting with the radical and producing something more stable. So once hydroquinone, and you don't need to know this reaction in particular, once hydroquinone reacts with a couple different radicals, it forms this interesting diradical that resonates to the much more stable benzoquinone. So this winds up being much, much more stable than any of the other radicals that were present. We are not terribly interested in the thermodynamic calculations, but what's interesting about this is it does help us to explain why bromination is more selective and more favorable than chlorination, and why we don't use this for fluorine or iodine. So if we look at just a little bit of, and I don't want to look at bond dissociation energies. Here we go. If we look at halogenation thermodynamics, we will see a great shift from fluorine to iodine. Well, first of all, iodine is endothermic, so it is just simply, it is not favorable to start with. You have to add energy to get that one to work. Fluorine is really exothermic, so that's too violent to work well. And chlorine and bromine are sort of in the middle there. They are exothermic, exergonic enough to go forward, but not so much that it is a violent reaction. All right, too exothermic, it's not practical. Endothermic, not favored, just simply doesn't occur. So only halogenation with Cl2 and Br2 are useful. We see that as kind of a theme throughout Organic 1. When you compare chlorine and bromine, so you don't need to know the numbers here, but let's talk through their thermodynamics. The first propagation step for chlorine is exothermic, as is the second propagation step. Bromine, the first step is endothermic, the second step is exothermic. So what we wind up seeing is that chlorine will just continue to react, giving itself plenty of energy. It actually makes it less selective. Bromine is overall exothermic, but it has a little bit more of a challenge within it. So it's much harder to get polybromination, right? Because with chlorination, right, you are very small activation energy. The products you make even lower energy, right? In this, it's like a waterfall. So it's just going to keep reacting. Bromination actually does require some energy, a little bit more energy, a little bit more oomph to get started. And it actually makes for a much more selective process. So this right here, these are transition states. But then here's your intermediate. So we're going to talk about those intermediates right there. When we look at the difference between chlorination and bromination, aside from the polyhalogenation issue, selectivity is another conversation that's really important. So when we were putting a halogen on methane, right, it doesn't really matter where the halogen goes. You're going to wind up with CH3X if you can stop it. If you're dealing with ethane, same thing. Let's not forget the light. If you can just put one halogen on there, you're going to get a one halo ethane. But what about when we have multiple places that the halogen could go? So that starts with propane. Chlorine could add to the 1 position or the 2 position, and you get a significant amount of both products. Even though the intermediate would tell you, right, this intermediate is more stable than this intermediate. But because the activation energy is so low for chlorination, they're both relatively easy to get to. So you get like a 60-40 split. That's a lot. If you're trying to make one specific halogenated product, that's a lot of waste, right? And then separating something that is this close together in structure would be difficult. Not impossible, but difficult. But look what happens when we switch to bromine. We now have a significant major product. And this has to do with something called the Hammond postulate, which I usually skip over, but this is the only place it comes back up. When you look at that energy diagram, since that transition state for, chlorination is much closer in energy to the reactants than the intermediates, it doesn't matter as much which intermediate you make, right? Because the Hammond postulate states that the transition state, the top of that energy diagram, is going to look more similar to whichever side it is closer to energetically. So it's closer in energy to the reactants. So that transition state is going to look more like the reactants in the intermediate. So the stability of the radical intermediate isn't as important. Whereas with bromination, the intermediates are higher in energy, so they're actually closer to the transition state, meaning that transition state looks more like the intermediates. So when we think about this radical versus this one, this is a lot more stable. So we are going to start selecting when we don't have as much energy. This is not as exothermic a step. In fact, the first step is not exothermic. The thermodynamics become much more important. And we can predict now what product we're going to get, which is really helpful when you're doing organic chemistry. So bromination, the takeaway, is more selective than chlorination. And so most of the time we do brominations. It's also important to note, let's see. So bromination and chlorination, if I ask for a major product, because even 60-40 is still, there's a major and a minor product. It's just way more favored with bromination with the 97 versus 3. The major product, if you are asked to predict, you are putting the halogen on the carbon. There we go. Where the radical would be most stable. Where the radical intermediate. So it's going to go to the most substituted position. Resonance may also be something to think about, but secondary is better than primary in the propane example. Would be most stable. So you can see here in the energy diagrams, the tertiary radical is definitely preferred for chlorination. It's just the secondary and the primary radical are all still similar or lower in energy to your starting materials. So it's just not that hard to get over this hump and get to any of those options. But for bromination, everything is higher in energy than your starting materials. So many more of your molecules are going to be able to get over that lower energy hump than the one to get to secondary or primary. So that bromine reaction is much more selective again. You see that start to be even more significant the more substituted a carbon is. And again, that just has to do with just how much more stable a tertiary radical is than a primary or secondary. So when we're dealing with chlorine, it's a little bit more selective, but still significant amounts of minor product. With bromine, by the time you get to a tertiary position, it's essentially 100% your major product, your more substituted product. The relative selectivity of bromine, right, is for, let's see, for the fastest product. We are comparing it to chlorination and the different, I feel like it's missing something here. I have a feeling they're just comparing to primary, secondary, tertiary. All right, 1,600 times faster at that tertiary position. And again, that has everything to do with the stability of the intermediate. I think that 1,600 came from... Oh, it came from another slide. All you need to know, too fast to work. Chlorine works, but the ratio of products is not super selective. Bromine works well, very selective for a major product. As far as stereochemistry is concerned, we think about that chiral center. If a new chiral center is formed, for instance, like in this reaction, you're going to get a mixture of products. It's not like an SN2, even though the radical isn't completely flat. The radical that is reacting with it can approach from either side, right? Because you can either think of it as totally flat or a really shallow pyramid that converts. So in either case, however you think about it, the approaching radical can come from either side. So it's not stereoselective at all. It's regioselective, but it is not stereoselective. So if you come to a question, I don't usually give wedges and dashes on my own questions. But if like in your homework you come across one, if it's asking for stereochemistry and you've made a new chiral center, you just have to show both. Okay, and so again, there is a chiral center that is made here. It can add from either side though, so it's just easiest to draw it flat or to draw both the wedge and the dash, or even that squiggly line I've told you about before. Okay, we will pick up with allylic halogenation in part 2.